They called it at 2:47 a.m. this morning. 3 separate observatories, different continents, all looking at the same object streaking through our solar system. And what they saw shouldn't be possible for something that's supposed to be dead. Because 3I/Atlas, the interstellar visitor that's been crossing our neighborhood for months, just changed direction. Again. Not because something hit it, not because of gravity, but because something inside it decided to wake up. And by the end of this video, you're going to understand why NASA scientists are now watching this thing 24/7, why they're scrambling for telescope time, and why the math that's supposed to predict where comets go just stopped working. Real quick, drop a comment right now and tell me, are you watching this on your phone or your computer? Just curious where everyone's tuning in from. All right, let's rewind. Because to understand what's happening right now, you need to see how we got here. So first things first, what even is 3I/Atlas? Back in early 2025, astronomers picked up something weird, a faint smudge moving through the sky faster than anything gravitationally bound to our sun should move. Within weeks, the orbital calculations came back definitive. This thing came from outside our solar system, interstellar, the third confirmed visitor we've ever tracked. They named it 3I/Atlas after the survey system that caught it. Now here's the thing about interstellar objects. They're supposed to be rare, like once in a decade rare, but we've now had 3 in just a few years. Oumuamua in 2017, 2I/Borisov in 2019, and now this. Each one teaches us something completely new about what's drifting between the stars, about what kinds of objects get kicked out of distant solar systems and sent wandering through the void for millions of years. But 3I/Atlas, this one's different. Because unlike Oumuamua, which was dark, silent, and tumbling like a cosmic cigar, 3I/Atlas is active. It's venting, glowing, throwing off gas and dust like a classic comet, which means it's got volatile ices inside, water, carbon dioxide, carbon monoxide, stuff that was frozen solid for eons in the cold of interstellar space. And now, our sun is waking it up. For the first few months, everything looked normal. I mean, as normal as an interstellar comet can look. Steady brightening as it approached the sun, a nice consistent coma, the fuzzy cloud of gas around the nucleus, a tail forming, jets of material streaming out. Observatories around the world were watching it closely, sure, but the excitement was controlled, scientific. This was a once-in-a-generation opportunity to study something born in another star system. The orbital calculations were holding steady. The models predicted its path with confidence. It was going to swing around the sun, give us a few months of incredible data, and then head back out into the void. A clean story, a predictable story. And then, 3 weeks ago, the first anomaly hit. It was subtle at first, so subtle that some astronomers thought it was measurement error. See, when you're tracking something millions of kilometers away, moving at tens of thousands of kilometers per hour, precision is everything. You're measuring tiny shifts in position against the background stars, fractions of an arcsecond. The math has to be perfect. And for weeks, the math was perfect. But then the orbital solution, the model that predicts where 3I/Atlas should be at any given time, started throwing warnings. The residuals were climbing. That's the difference between where the model says it should be and where it actually is. At first, the difference was tiny, a few hundredths of an arcsecond. Background noise maybe, atmospheric distortion, telescope calibration drift. But then more observations came in, and the pattern held. The comet wasn't where it was supposed to be. It had drifted, not much, but measurably, consistently, in a specific direction. And here's the kicker. That direction didn't match what gravity alone could explain. The sun's pull? Accounted for. Jupiter's influence? Accounted for. Every planet, every gravitational tug from every massive body in the solar system, all in the model. And still, 3I/Atlas was off course. That's when the terms started showing up in the alerts. non-gravitational acceleration. Okay, pause. Let me explain what that means, because this is where it gets wild. When a comet, especially an active one, gets close to the sun, the heat doesn't just make it glow, it makes it move. Here's how. The nucleus of a comet is basically a dirty snowball, ices mixed with rock and dust. When sunlight hits it, those ices don't melt, they sublimate. They go straight from solid to gas. And that gas doesn't just sit there, it erupts. Jets, geysers, plumes of vapor and dust blasting out at hundreds of meters per second. And here's the thing about Newton's third law. Every action has an equal and opposite reaction. So when gas shoots out one side of the nucleus gets pushed the other way, like a tiny thruster, a rocket engine made of ice and sunlight. It's called a non-gravitational force, and it's real, it's measurable, and it's why tracking comets precisely is so damn hard. For 3I/Atlas, scientists had already factored this in. They'd measured the main jet, they'd calculated the thrust, they'd added it to the model. And for a while, everything balanced, until it didn't. Because 3 weeks ago, the non-gravitational force changed. The jet was still there, still venting, but the direction of the push rotated. Not by a lot, but just a few degrees, but enough to throw off every prediction. And that's when NASA started paying closer attention. Because when a comet's thrust vector changes, usually it means something inside the nucleus changed first.
So here's where the story accelerates. After that first shift 3 weeks ago, the observatories tightened their watch. More telescope time, more frequent measurements, higher resolution imaging. They wanted to see if this was a one-time adjustment or the start of something bigger. And for about 10 days, it looked stable again. The new thrust direction held steady, the orbit predictions started converging, everyone exhaled a little. Maybe it was just a single event, a crack opening, a new vent activating. The comet found a new equilibrium, and now it would coast peacefully toward its exit from the solar system. That's what they hoped. That's not what happened. Because 8 days ago, it shifted again. This time, the alert came faster. The orbital team didn't wait for days of data to pile up. They saw the residual spike, ran the numbers, and knew immediately. The non-gravitational acceleration had rotated again. Different direction, different magnitude. The comet was pushing itself in a new way. And this time, they had something they didn't have before. High-resolution images from multiple observatories, all processed and stacked to reveal the fine structure of the inner coma. And those images confirmed it. The jets had moved. Not the same jets in a new orientation, not a subtle tilt. The whole outgassing pattern had reorganized. The main jet, the dominant stream that had been steady for weeks, had weakened, and 2 secondary jets, previously faint, had intensified. It was like watching the comet rearrange itself. One astronomer described it like this. Imagine you're watching a fire. You think you understand where the flames are strongest, and then, overnight, the fuel shifts, the flames move, the heat redistributes, and suddenly, the fire is burning in a completely different pattern. That's what was happening to 3I Atlas. Something inside the nucleus, hidden beneath the surface, was evolving, and every time it changed, the comet's behavior changed with it. The orbit shifted, the jets reorganized, the predictions broke. Now, at this point, you might be thinking, okay, so comets are dynamic. They change. That's not exactly news, right? And you'd be right. Solar system comets do this all the time. Vents open and close, jets flare and fade. It's chaotic, sure, but it's expected. But here's the difference. 3I Atlas isn't a solar system comet. It didn't form in the same disk of gas and dust that made our planets. It didn't grow up under our sun's radiation. It spent millions, maybe billions of years drifting through interstellar space, frozen solid, at just a few degrees above absolute zero. Its composition? Unknown. Its internal structure? A guess. The way it responds to solar heating? Completely unpredictable. We're watching an alien object, literally from another star system, react to our sun for the first time in its existence. And every assumption we've made based on solar system comets might not apply.
So when 3I Atlas shifted once, scientists were curious. When it shifted twice, they were concerned. And then, last night, it shifted a third time. That's what this morning's alert was about. Fresh positional measurements came in from tracking stations across the globe. Same telescopes, same reduction methods, same targets. And when the data hit the orbit solver, the fit shattered. The residuals spiked higher than they'd ever been. The non-gravitational acceleration had rotated again, this time more dramatically than before. And the model that had been painstakingly rebuilt after the last shift? Useless. They had to start over, recalculate the thrust vector, refit the orbit, rerun the predictions. And while they were doing that, the imaging teams sent over their latest stacks. And the images were unsettling. The inner coma, the bright glowing region closest to the nucleus, had changed shape. It was no longer centered around the nucleus the way you'd expect. It was skewed, asymmetric, like the brightest part of the glow had shifted to one side. The main jet, which had already moved once, had moved again. And this time, it wasn't just a tilt, it was leaning in a completely new direction compared to last week. But that wasn't the strangest part. The strangest part were the secondary features, smaller jets, faint fans of material, little streamers that had been barely visible before. They'd all rebalanced. It was like the whole system had twisted, rotated, reorganized around a new center of activity. And the tail, the long, sweeping tail of dust and gas trailing behind the comet, had developed a subtle curve, an S shape that definitely wasn't there a week ago. One astronomer put it bluntly. This doesn't look like a comet settling down. This looks like a comet in transition. Transition to what? That's the question no one wants to say out loud. But I will, because by the end of this video, you need to understand what's really at stake here. Here's what makes this morning's alert so significant. It's not just one team saying, hey, something changed. It's two completely independent lines of evidence from two completely separate teams using totally different methods, arriving at the exact same conclusion. The orbital team is looking at positions, math, residuals, gravitational models. They don't care about images. They care about where the comet is versus where it should be. The imaging team is looking at light, structure, jets, dust. They don't care about orbits, they care about what the comet looks like. And both teams, working separately, processing different data sets, came to NASA with the same message. 3I Atlas changed again. And it's not slowing down. That's not coincidence. That's not error. That's real. And when NASA sees two independent confirmations of the same phenomenon, they don't just take notes, they mobilize.
What's inside a comet nucleus? All right, let's dig into the science. Because if you want to understand what's happening to 3I/ATLS, you need to understand what a comet nucleus actually is. And here's the truth. It's not solid. When people think comet, they picture a rock, a boulder, something dense and strong, hurtling through space. Nope. A comet nucleus is more like a fragile pile of rubble, held together by weak gravity and even weaker ice cohesion. It's porous, full of voids, structurally unstable. Think of it like this. Imagine taking gravel, sand, chunks of ice, and frozen dirt, then loosely packing it all together in the freezer for 1,000,000 years. Then you pull it out and throw it at the sun. That's a comet. The surface is dark, almost black, because over time, solar radiation and cosmic rays cook the outer layer into a crust of radiation-processed organics, tar-like, low reflectivity. But underneath, that's where the volatile ices live. Water ice, frozen carbon dioxide, carbon monoxide, methane, all the light, reactive stuff that was trapped when the comet formed in the cold outer reaches of some distant star system. And as the comet gets closer to the sun, that crust heats up, slowly. The heat sinks inward, millimeter by millimeter, day by day. And when the heat finally reaches those buried ices, they sublimate, solid to gas, instantly. Pressure builds, cracks form, weak spots fail, and then, boom, a vent erupts. Gas and dust blast out at hundreds of meters per second. That's a jet. And here's the key point.
Jets don't erupt evenly across the whole nucleus. They're localized, specific fractures, specific pockets of ice, specific weak points in the crust. So the outgassing pattern, the map of where the jets are firing, tells you something about the internal structure of the nucleus. And when that pattern changes, it means the internal structure is changing too. Why the thrust vector keeps rotating? So, why this 3I/ATLS keeps shifting? There are two main explanations, and both of them fit the data. The scary part? They can both be happening at the same time. Explanation 1. New vents are opening. Remember, 3I/ATLS has been heating up for months. The heat has been sinking deeper and deeper into the nucleus, and not all pockets of volatile ice are at the same depth. Some were close to the surface. Those vented early, weeks ago. That was the first jet, the dominant one that gave us the initial non-gravitational force. But deeper pockets? They're just now reaching their breaking point. Pressure builds, the crust above them weakens, and eventually, crack. A new vent blows. And if that new vent is strong enough, it can rival or even overpower the old one. And the moment that happens, the net thrust vector rotates. Because now you've got two jets pushing in different directions, and the sum of those forces points somewhere new. That shifts the orbit, that reorganizes the coma. That's what we're seeing in the images. Explanation 2. The nucleus is tumbling. But here's the thing. Even if no new vents open, the thrust vector can still change. Because the nucleus isn't sitting still. It's rotating, spinning through space. And comets don't spin cleanly. They tumble, they wobble, they precess like a tilted top winding down. And if the spin axis is changing, if the nucleus is tumbling chaotically, then the jets don't need to move for the thrust direction to shift, because the whole object is reorienting in space. Imagine you're holding a garden hose. Water's spraying out, now starts spinning in place. The direction the water shoots changes, right? Even though the hose itself didn't move. Same idea. If the nucleus is tumbling, the jets stay in the same spot on the surface, but the direction they point changes as the nucleus rotates. And here's the kicker. Jets create torque. Every time gas shoots out, it applies a twisting force to the nucleus. Over thousands of rotations, that torque adds up. It changes the spin rate. It changes the orientation. So the jets cause the tumbling, and the tumbling changes the jets. It's a feedback loop. And once that loop starts, it's really hard to stop. Now here's where it gets uncomfortable. Every time the thrust vector changes, stress changes inside the nucleus. Think about it. You've got jets firing, gas escaping, mass being removed from specific locations. That shifts the mass distribution. That shifts the center of gravity. Cracks that were stable under one stress regime suddenly aren't. Cavities compress, surfaces weaken. The whole structure adjusts. And remember, this nucleus is weak. It's not held together by rock. It's held together by barely frozen ice and a gravitational force so feeble you could probably jump off the surface and never come back. It's fragile, delicate, barely cohesive. And it's being shaken apart from the inside. We've seen this pattern before with solar system comets. Subtle changes in non-gravitational forces, shifting jets, spin rates drifting, and then, sometimes without warning, breakup. The nucleus splits, chunks separate. Sometimes it disintegrates entirely into a cloud of fragments and dust, just falls apart, spreads into a diffuse stream that fades over days or weeks. Comets die like this. We've watched it happen. We've documented it. It's not hypothetical, it's real. And the pattern 3I/ATLS is showing right now, it looks uncomfortably similar. Now, to be clear, NASA isn't predicting that 3I/ATLS is about to disintegrate. The official language is careful, professional. Updated orbital solution, evolving non-gravitational acceleration, continued monitoring recommended. But let's be honest about one thing. You don't scramble for extra telescope time because you think the story is winding down. You don't push for denser measurements because you think everything is stable. You do it because you think something might be developing, something significant, something you don't want to miss. And when NASA starts using phrases like evolving non-gravitational acceleration and structural monitoring protocols, they're watching for signs of instability. They're watching to see if 3I/ATLS holds together, or if it doesn't.
So here we are, 3 shifts in 3 weeks, each one more dramatic than the last. And the question hanging in the air, the question no one wants to ask directly, is this: are we watching 3I Atlas adapt or unravel? Because here's the thing, right now we're at a tipping point, and we genuinely don't know which way it goes. Scenario 1, stabilization. Maybe this is just adjustment. The nucleus is responding to solar heating in a chaotic but ultimately manageable way. New vents open, the system rebalances, and eventually it settles into a final configuration. The jets stabilize, the spin steadies, the orbit locks into a predictable path, and 3I Atlas coasts peacefully out of the solar system back into the void, no worse for wear. That's the hopeful scenario. That's what everyone's rooting for. Scenario 2, escalation. But what if it doesn't stabilize? What if the shifts keep coming? What if the next alert 3 days from now, a week from now, says the thrust vector rotated again, and the images show another reorganization? More jets, more asymmetry, more stress. Then the small changes aren't small anymore. They're steps, a progression, building towards something. And if that something is structural failure, if the nucleus can't handle the internal pressure and the external torque and the thermal stress all at once, then we might be watching the death of an interstellar comet in real time. And that is why this is the most important story in astronomy right now. Now, some of you might be thinking, okay, sure, it's fascinating, but why does it matter? Why should I care if an interstellar comet holds together or falls apart? Fair question. Let me tell you why. First, this is the only chance we get. 3I Atlas is here, right now, reacting to our sun, giving us data we've never had before about an object from another star system. And once it leaves, and it will leave, we probably won't see another interstellar comet for years, maybe decades. If it disintegrates before we finish studying it, that data is gone. We lose the opportunity to understand how interstellar material behaves under solar heating, what it's made of, how it formed, what conditions were like in the star system it came from. This is a once-in-a-lifetime opportunity, maybe once in a generation, and the clock is ticking. Second, this tells us something profound about planetary system formation. Every comet, whether from our solar system or another, is a time capsule. It formed billions of years ago from the leftover material of star and planet formation. It's been frozen, unchanged ever since. Studying it is like studying the raw ingredients of worlds, the stuff planets are made from, the ices and organics that seed atmospheres and oceans. If 3I Atlas is compositionally different from our comets, and early spectroscopy suggests it might be, then it tells us that other star systems build planets differently, with different chemistry, different abundances, different building blocks. And that has huge implications for the search for life, for understanding habitability, for knowing what kinds of worlds are out there. Third, this is just rare. Look, we live in an era where we can watch an interstellar object react to our sun in real time. We can track its orbit to the meter, image its jets, measure its spin, watch it evolve day by day. 50 years ago, this would have been impossible. 100 years ago, unimaginable. And even now, in 2025, this is only the third interstellar object we've ever tracked. The first one that's active, the first one showing this kind of dynamic behavior. We're witnessing history, astronomical history. And whether it stabilizes or falls apart, we're going to learn something we didn't know before. So, let me bring this full circle. At the beginning of this video, I told you something inside 3I Atlas decided to wake up, and I promised you'd understand why by the end. Here's the truth. 3I Atlas didn't wake up. It's been awake the whole time, venting,
active, responding to the sun. What changed is this. We're now realizing that what we thought was a stable, predictable process isn't. The nucleus isn't just passively outgassing, it's reorganizing, layer by layer, vent by vent, rotation by rotation. And every time it reorganizes, it pushes itself in a new direction. It changes its own orbit. It rewrites its own trajectory. That's what's happening. That's what shifting course really means. 3I Atlas isn't being steered by gravity anymore. It's steering itself through internal forces we can't see, driven by a structure we don't fully understand. And the only question that matters now, is whether that process stabilizes or spirals. Because if the next update says the thrust vector rotated again, and the next images show more jets, more asymmetry, more stress, then we'll know. We're not watching adaptation, we're watching the beginning of the end. So, where are we right now? What's the latest? As of this morning, literally hours ago, 3I Atlas is still intact, still active, still venting. Observatories around the world are monitoring it 24/7. Every clear night, more data, sharper images, refined models. The orbital solution has been updated to account for the latest shift. The new thrust vector is characterized, the predictions are converged, for now. But the teams aren't relaxing, because they know what I just told you. If this is a pattern, if the shifts keep coming, then the next one could happen any day. And when it does, the alerts will go out again. The data will be processed again. The models will be rebuilt again. Until either the comet settles down or it doesn't. Here's what I want you to take away from this. 3I Atlas is not just a scientific curiosity. It's a messenger, a visitor from another star system carrying information about worlds we'll never reach. And right now, it's giving us that information in real time, through its orbit, through its jets, through the way it responds to our sun. Whether it survives or disintegrates, we're going to learn. And what we learn could reshape how we think about planetary systems, comet formation, and the diversity of objects drifting through the galaxy. But more than that, this is a reminder. The universe is not static, it's not predictable, it's not tame. Even when we think we understand something, even when the models hold steady and the predictions converge, nature can surprise us. A crack opens, a vent blows, a nucleus shifts, and suddenly we're scrambling to keep up. That's the beauty of it. That's the thrill. That's why we watch the skies. Because every now and then, something out there reminds us just how much we still have to learn. So, what happens next? Honestly, we wait, we watch, we gather data. In a few days, maybe a week, there'll be another update, another batch of observations, another alert, or maybe, hopefully, an all clear. And when that update comes, I'll be here to break it down, to explain what it means, to connect the dots. So, if you want to stay updated on 3I Atlas, if you want to know whether it stabilizes or spirals, make sure you're subscribed. Hit that notification bell, because this story is far from over. And hey, drop a comment. Tell me, do you think 3I Atlas is going to hold together, or are we about to watch an interstellar breakup? I want to hear your predictions, because in a few weeks, we'll know who was right. Until then, keep looking up. The universe is full of surprises. And right now, one of those surprises is hurtling through our solar system, changing its mind every few days about where it wants to go. Thanks for watching. I'll see you in the next one.